Okay, so the next speaker is Sumilan Banerjee from Indian Institute of Science, speaking about is many body localization stable in d greater than 1?
Okay, thanks, Manas. Okay, so I'd first, of course, begin by thanking the organizers, especially Manas, for giving me opportunity to speak here. And this was really very nice conference and school, but unfortunately I couldn't attend much of it because of teaching responsibilities. Or just semester just started, but I'm just trying to look at all the YouTube videos once they come. So I really do not work on integrability as much, like standard usual integrability that we are hearing about here. But I have been working a little bit on many body localization, and something that I thought might be relevant for this, because this many body localization also has a concept of emergent integrability. And here the question of many body localization versus thermalization is whether these emergent integrals of motions, they are stable or not. Okay, so that's the question, and we are going to ask this question in higher dimension, a dimension higher than 1, and so that's the talk. So let me begin by acknowledging my collaborators. So this work has been done with Ehud Altman, and okay, I can't pronounce his name, Dragos. So both are from UC Berkeley. So it's really wonderful working with them. So this work that we have been doing for some time, it's okay. So since we will be talking about many body localization, and of course there are many talks or several speaker mentioned or talked about it. For example, Joel talked about many body localization at length. But still, just to set the stage, I mean, introduce a little bit of things that we'll be using for discussing this topic. The obvious starting point, as usual, always starts with this Anderson localization. And as we know that in 1958, Anderson gave this radically new idea that quantum states of even non-interacting electrons can have very completely two different, qualitatively different quantum states for some quantum particles or waves even moving in some random medium. These are these two cases, the localized and extended. So localized states, which are in some disordered system, they chooses a particular position in space, and then the wave function decays from that. And the other case is the extended state, which is the connected with the usual block waves, where the amplitude of this of wave functions is completely, more or less completely determined by the normalization for a system size L. Okay, so these are the two things, and we have, I mean, there has been huge number of studied, nicely reviewed in many reviews and other things. Now, just to introduce the question of many body localization in this language. So the idea is that if you start with this non-interacting system, so let's say some tight binding model, and then you have some random on-site potentials, which is drawn from some distribution, some random variables over some with some strength W. And then, of course, this will lead to, if you, for example, since this is a quadratic problem, at least in a computer, you can diagonalize it for finite system and look at the eigen functions. And if you have sufficiently strong disorder in higher dimension, or if you are in low dimension, then always you will find that that the states are localized and described by this form. Now the question, so the question of many body localization is that if you add some generic interaction term to this model, for example, this for this spinless muons, if you add some density-density interaction, then again, I mean, what you can try to do is that you can try to write down this thing using this single particle localized basis. And generically, you will get some term which essentially will connect all these different single particle localized orbitals. And so it's not at all obvious that since now this term will induce transition elements between different many-body space. So, for example, you start with this this localized orbital and construct some Slater determinants. Those for the non-interacting case will be also localized. Of course, will be localized, but now due to this matrix element between these states, it is not at all obvious that this thing can be stable, even though this basis you are using is localized. And in particular, generically, this kind of matrix elements will connect exponentially large number of states, that is in the many-body Hilbert space. And it's a valid question that can localization survive? Because to survive that somehow, I mean, you have to have so essentially, since almost all states are connected by this, so this matrix element somehow has to vanish, or this, in other words, the resonance between many body states has to go to zero in some way to have many localization being stable even in the presence of interaction. Now, anyway, so this is a complicated question to answer, and to some extent it was answered, at least perturbatively, that by these people in this quite famous paper, that the answer is yes, and sufficiently strong disorder. For example, if you start with all single particle states localized, then you can argue perturbatively that localization will be stable. And later, of course, people have studied this problem numerically, mostly in one-dimensional system using technique like exact diagonalization and matrix product state-based algorithm. And the phase diagram, mostly, I mean, this was based on the perturbative argument by Basco, Lehner, and Essler, and this paper, but also confirmed to some extent by numerical techniques that the generic phase diagram of this kind of interacting disorder system is this. So what we are plotting here in the y-axis is the energy, many-body energy or many-body energy density, let's say, which you can connect to some equivalent temperature if you try to use a ensemble to describe this energy. So there is some so this is a temperature or energy density axis, and as a function of disorder strength for a fixed interaction, the generic picture is something like that, there will be some demarcation between two types of states, one which is thermalizing or delocalized, and other is localized, and there are different characteristics of this. So first of all, of course, this localized state is in contrast to the thermalizing or metallic state, doesn't thermalize, and this probably is related to also the fact that there will be no transport. For example, whatever conserved quantities if you have some conserved quantities, the corresponding transport coefficients will be zero in this localized state, and those will be non-zero here. So that's the basic picture. Of course, there are issues whether even in one dimension this many-body mobility edge exists or not. That's still unresolved as far as I understand. So it could be that this phase diagram is not completely correct, and there is no many-body mobility edge. There is only a transition from all states localized to all states delocalized. So that possibility even in 1D exists. So people have proposed that this idea of mobility edge is in contradiction. So you can show that there is some contradiction if you assume there is a mobility edge. But we will not discuss about this today. So we are going to discuss about a problem. So this now if you ask that what is the basis of this phase diagram, so how do you know that this is true? I already discussed. I mean, these are based on numerics and this perturbative argument. Just to summarize, the existence of, if you ask what is the proof of existence of MBL, so it's mostly in one dimension. So there is numerical evidence that a lot of numerical work has given. But more importantly, probably for certain model, mainly some Ising model with both Wiegmann and transverse term, there is a mathematical proof in one dimension that you can construct this, which I will discuss, these local integrals of motions, at least for a certain model, and show that indeed there is MBL. So this is in 1D. Now, in general dimension, if you ask about higher dimension, then only proof, if you take it as a proof, is this perturbative proof, which was given by Basco-Alliner and Alsular and Gorny, Milling, Polyakov. And that essentially based on, again, some perturbative argument. Now, the perturbative treatment, of course, was extremely non-trivial. But I mean, just to give a very crude idea, the perturbative treatment was based on this idea that your interaction is weak in some sense, and namely it is weaker compared to some scale which is given by disorder. And this scale, so P is, for example, is your interaction strength, and delta xi is essentially some level spacing, single particle level spacing over a localization volume. Okay, so if you have single particle localization, so you start with all single particle state localized, there is a localization length, and that gives you some single particle level spacing. So when this quantity is small, then this perturbative proof works. Now the question that some people started asking recently is that are there so can you come up with some non-perturbative effect where presumably this criteria is not valid, and this non-perturbative effect can, if you can then show that destabilizes MBL in any dimension, specifically in higher dimension. So that is the idea, and it turns out that there is at least one argument which it's not mathematically rigorous, but quite sensible and reasonable argument that I will discuss here. And that's the main topic of this talk, which was given by these people, Wojciech Diroek and Francois Fuvenius. So the idea was that you try to come up with some kind of instability, or probable instability of a otherwise localized state. And so this is the particular instability they consider. So what is drawn here? So this dots are essentially, I will discuss. These are these local integrals of motions, so which you can define in a MBL state. And so the idea is that more or less everywhere in the system, this criteria is, let's say, satisfied. So Basco-Alliner, Alsular will tell you that it's a localized state. But this system is thermodynamically large. Okay, so if you have thermodynamically large system, then there is always a finite probability of having a large, though finite region where this criteria is not satisfied. Okay, so this is a rare region of disorder where you assume that disorder is weaker compared to the interaction in the system. And that such region will always come with some small but finite probability in such a system. And then the idea is that, so this local region is finite, but locally it will look thermal and it will look like a finite bath, finite but quite large bath. Now the question they ask that if you take this thing and if you try to ask that, so this kind of bubble, so they call it a thermal bubble or something. So whether MBL or localized state is actually stable to such a region. Okay, such a rare region. So that's the question of this argument, which I will discuss here. So that's the outline of the talk. So I'm going to discuss this argument and trying to test this argument, some of the assumptions of this argument in this talk. So I have already given a definition, introduced a little bit about MBL. So I'll discuss few more things which will be helpful in our discussion. And then I will discuss mostly this rare region instability argument that was given by these people. And then we'll try to test some of these assumptions of these arguments using exact diagonalization, which I will discuss this. And then we'll see that these exact diagonalization studies are limited, of course, to very small system size. So you cannot really conclusively prove or disprove their arguments, but you can say whether they're at least consistent within small system. So we'll come up with some toy model to also test some of the assumptions, and I'll show that there could be some possibility that some of the assumptions may not be valid, and then I'll conclude. So that's the outline. Okay. So okay, so these I already discussed. So the models for the MBL that we'll also use, or people generally use, that the most simplest model that you can write, and these are mostly in one dimension. So you can either write in terms of spins or fermions. and in one dimension, so you can connect them using standard Jordan-Wigner transformation. So typically, this model I already showed, and this is related to this this XXG model that we are hearing in this in this conference a lot. Only thing is here we will consider a random Wiegmann term, which is acts as the source of disorder, which is related to this one. And then there are of course other things. And in general, what we are interested in this MBL question is interested in this many-body eigenstates. And we want to discuss the localization and thermalization properties of these eigenstates. So that's the standard question of MBL. And this is of course I mean this as we know that this if you talk about a single eigenstate, there is a way to define even for a single eigenstate the sense of thermalization, and the idea came from this eigenstate thermalization hypothesis. And the idea is that if you take some high energy eigenstates somewhere in the middle of the spectrum, for let's say some bounded spectrum, then they're very dense. But let's say if you look at one eigenstate and so this is the system, and you divide into two parts, A and B, then the idea is you can generate a partial density matrix, reduced density matrix for some subvolume A. And if this eigenstate satisfy this eigenstate thermalization, then one criteria would be that it will, if you have a sufficiently large subvolume, then where this surface terms, etc., are not important, then this density matrix, this reduced density matrix will look like a thermal density matrix. And similarly, as a consequence, also, if you define an entanglement entropy of this state, then the entanglement entropy should be same as the thermal entropy of that energy at that energy density. And so it has to satisfy volume law with the precise coefficients, which is exactly thermal coefficient. So that's the definition of this eigenstate thermalization. Now the idea of, so the way you define MBL is based on basically lack of this thermalization. So essentially you tells that the MBL, the definition of MBL is when ETH fails. So that's probably the best definition till now we have, if you have to define thermalization of eigenstates. Now, so here, so the question is, why do you have such a area law and things like that? So it turns out that there is a simple understanding of these properties based on this idea of effective model of MBL, and which is related to this emergent integrability. So if you start with such a model, generic interacting model, let's say you have written in the basis of these localized orbitals, you have some term which is just diagonal in the single particle basis, and then you have this interacting term. So this, for example, these operators are related to the original operators on the side basis through these localized wave functions. Now it turns out the idea that you have this MBL state is related to the fact that in the MBL phase, you will have in the MBL fixed point, there will be this emergent integrability. You will have infinite number of, extensive number of this quasi-local integrals of motions. For example, in this model, they will be related to some number operators, let's say some, and which are also called L bits or LIOMs. And the idea is that once you have this fixed point, then this Hamiltonian reduces to some effective Hamiltonian, which has only terms which commutes with each other. I mean, so the whole Hamiltonian commutes with each of these number operators. So essentially, you have all these integrals of motions. And this is, of course, the property of a particular phase, not the property of the original model, unlike the standard integrable models. So these are emergent as a result. And one of the ways, for example, to construct this is what roughly Basco, Adener, and Alsula did, was to construct this perturbatively, these operators, and then you can construct these integrals of motions perturbatively. And idea of many body localization is to argue that this series essentially converges, and that will be the stability of MBL. Okay, so there are other ways to construct these integrals of motions, even when interaction is not very weak. But if you assume that there is MBL phase, then you can construct it using this real space strong disorder RG techniques that people have done. Okay, so there are different ways of constructing this. Now, so as a result of these integrals of motions, there are certain diagnostic that you can obtain for MBL versus thermal state. So one of the ways to distinguish, so if you want to calculate some quantity, for example, so you of course can look at eigenstates and look at their statistics and entanglement entropy. Other things that you can calculate is, for example, some local spectral function of a given eigenstate, which is defined like this. And the characteristic of the MBL would be these local spectral functions will have poles even for this infinite system, even in the presence of interactions. And when you have a thermal state, then this will become a continuum spectrum. Essentially, it will have branch curves, and so this discrete pole structure will go away. However, one thing is that typically when we look at spectral functions in standard techniques, we calculate the spectral function in some thermal ensemble, and that will be essentially this summation, this thermal summation of this eigenstate spectral function. And it can be argued that even if you have an MBL state, if you construct such a thermal spectral function, it will lose all information about localization. So if you look at some thermal spectrum function of a MBL state, you will not be able to tell the difference between a localized and a thermal state. So really you need to calculate a spectral function of a given eigenstate. You can't really calculate the thermal spectral function. So of course there are some MBL systems where you can still have some information, but there are some special systems which are called strong MBL. But most of the MBL system you can't distinguish. So the reason I am talking about this, because we'll be using these spectral functions, and this will be also in some important aspect of our discussion. So that's why I just discussed this. Now, and of course, for the delocalized state, this thermal spectral function and the eigenstate spectral function for a given energy density will be same. So they will be exactly same, but for the MBL state, there will be a difference, and that will distinguish this. Yes. So it is defined, so you define this Green's function, this is just single particle Green's function, and then you take the Fourier transform of this, and you obtain the imaginary part. Just standard density of states, spectral density that you calculate. So it's just that. Okay. So there are some, anyways, I'll not go into this. So there are other distinctions of MBL states, and you might have seen in this conference, people have talked about it. So now let's get to this issue that I started with, which is about this rare region instability argument. So let me at least try to tell what is this argument, which tells that there will be no MBL in higher dimension. Okay, so that's the question, and the argument was given by these people. So let's look at the argument. So to look at the argument, you try to come up with a simple toy model which is generic enough. And the way you do it is you assume that you have some, you assume that there is MBL in any dimension. Okay, so you start with this assumption. So you have some local orbitals or some integrals of motions that you can define. And then, as I told, that for a thermodynamically large system, there could be always a region which is where it's a rare region where the disorder is extremely weak. Okay. So you can have a thermal region. So the way you model this situation is you say that the total Hamiltonian consists of essentially three parts. So you have something here which I call HB, which corresponds to this bubble, and then there is a localized insulator around it. So that's Hamiltonian is described by this, and then there is a coupling between them. Okay, that's the standard thing. So now the way you use this argument is use some simple model of this thermal region. So in particular, what they used is a random matrix to describe this, say a GOE random matrix to describe this thermal region. So you essentially take a completely featureless random matrix. So this is a random matrix in this. So let's say you have n number of sites. So if you think in terms of fermions in this region, in this rare region, and then this matrix that you have will have 2 to the power n cross 2 to the power n matrix in this Hilbert space. So you can define a particular well-defined Hilbert space here, for example, the occupation basis. And so that's the description of this thermal region. Okay, so you describe it in terms of a random matrix, and the one important thing here would be is the level spacing, the many body level spacing of this region, and that many body level spacing will be some many body bandwidth divided by 2 to the power n, which is the dimension of the Hilbert space, and this is the many body level spacing when you are at infinite temperature or in the high temperature. Of course, at lower energy densities, this will not be the case, but we are only interested in this kind of high energy states, finite energy density states. So that's the description of this GOE of the thermal thing, and the MBL you describe using this effective model that I described earlier, which is written in terms of this emergent integrals of motions, these LIOMs. This quantities, so you can define this number operators in terms of these fermionic operators, and as I told that perturbatively, for example, you can construct this operator which will be related to your original fermionic operator through the localized eigenfunction. Now, to do the argument, you actually do one extreme thing. You actually neglect completely this term which comes due to interaction. So in other words, what we are actually taking a Anderson insulator, and immersed in the Anderson insulator is this thermal region. And what this argument is going to show is that even Anderson insulator is unstable if you have a finite interacting thermal region. Of course, it looks impossible because you have an Anderson insulator, infinitely large non-interacting insulator, and the argument tries to tell that truly there cannot be MBL state in principle even if you have a finite region in this infinite system which is interacting. Yes.
Shimla, so this is Anderson insulator in these new variables, right? This tilde.
No, even in the old variable. So for example, for the Anderson insulator, you can construct these local integrals of motions, right? So those are just the non-interacting orbitals.
Right.
So let's say for the Anderson case, just assume that this is the single particle diagonal basis, right? So that's what we are just taking eventually.
No, I'm just confused about, so you had C tilde written in terms of C plus corrections, right? And N tilde is supposed to be C tilde C.
That's right. So, but here, so when you take the interaction to 0, then these dots are actually 0. So basically, you're right. So I have some expansion, right? And this, so if you just had non-interacting case, then this is just a unitary transformation, right, between the single particle basis. If you have interaction, then there is this additional term that I showed. But if you take interaction to be 0, there is no term. So in the non-interacting case, they just smoothly go into the standard trivial integrals of motions of this non-interacting mode. So we are eventually just taking a non-interacting Anderson insulator and just inserting a thermal region in the middle of it. So that's what we are doing. Okay, does it make sense?
Why do you call it MBL? I'm not.
No, it's not MBL. So you can think that Anderson insulator is extreme limit of MBL, right? Where interaction is. So so this argument, what it tries to do is the worst case scenario for thermalization, right? Is assume that I take the best possible Anderson insulator I have, which is the non-interacting Anderson insulator, and if I try to show even that is unstable, then it's highly likely that when you put interaction, that will of course still be unstable. Okay, so that's the way this argument tries to go about. Yes. Yeah, so system is infinite and bubble is small, meaning it's a finite, it could be large, but it's not infinity. It's always some finite size. Super spin, no, you will want to define one single variable for this. No, this is a consist of large number of sites and this n could be large. I mean, it's not infinite, but it could be arbitrarily large. So, I mean, how do you define a super spin for the, I mean, it's a generic interacting region. So define, for example, here define through some random matrix. I'm not sure how do you define a single super spin to describe this. Yeah, that's what I'm doing, right? So that's what. So the local Hilbert space. So this n refers to the n number of sites, or it could be n number of spins. Okay, so that's fine. So we can actually do this whole thing in terms of spins. And the local Hilbert space is the Hilbert space of spin. In fact, for this spinless fermion, it's also 2 to the power n, and if you have spin half, it will also be 2 to the power n. No. So one large spin. So there is something. So here, important thing is that this bubble has a many body level spacing. Okay, if you define it as a one spin somehow, so then it will not be able to do it. I mean, so this, okay, it may, I mean, there are some works in that along that line, like one central spin coupled to this localized basis, and even that can destabilize if you couple it strong enough. But the kind of coupling we are taking, then it will not be enough. Yeah. So this many body aspect is important. I mean, for example, if you had a non-interacting delocalized metal here, it would not do. Okay. This argument will not go. This fact that you have exponentially small level spacing is important. Okay. So now you couple. So of course, so these are the localized states, and these are the bubble that we have defined. And the only thing you need to do is couple this new localized orbital to these bubbles, and that you can easily argue that is essentially this coupling is determined by the localized eigenfunctions, single particle eigenfunctions, right? So it's just by some unitary transformation, and as a result, what will happen is that you can define these dots, which are these local integrals of motions at different distances, and their coupling with this bubble in the interacting region. So all of them are now coupled by this due to this transformation, because you have gone to this basis. All of them are coupled, but this coupling become exponentially small as you go away from this region. Okay, so that's the trick that if you started tried to do this thing with the original side basis, then it will be more harder to do. So this is the thing they came up with. So you now have all these integrals of motions coupled, but this coupling is going exponentially small as a function of distance. So the question is that can a single bubble destroy this entire MBL system? And that's the argument. The answer is seems to be yes in higher dimension, and that's the argument that now I'm going to give. So let me show how the argument works. So the argument works through some kind of bootstrap procedure. So the way you do is you do one step at a time. So you first consider this bubble and disregard all local integrals of motion except the one which is the closest. And that one is has the strongest coupling with this bubble. Okay, the coupling that I showed, which was exponentially decaying. So let's say you take the strongest coupled one. So given this, you can estimate some kind of matrix element between of this. So this C1 is one of the operator in the bubble. Okay, and due to this coupling, so I'll come to that. But what you need to need to ask here is that this LIOM or localized integrals of motions, which was localized without the coupling of this, meaning they are conserved as a function of time. Now, due to this coupling, there could be a Fermi golden rule rate, meaning that it can go into this and get lost in this thermal bubble. So essentially, in other words, it can decay. Okay, so now it is with this coupling, it is no longer, because it's just like a local integral of motion coupled to a bath. Although the bath is of finite size, but very large bath. So then it can give a decay to this quantum bit. Okay, so the way you estimate the decay is you need to estimate some matrix element between transitions between. So this decay will come from some transition in this bubble, which is from some many-body eigenstate of this bubble to other bubble, and that will give a transition to this, the number of this quantum bit. So that's the process, and this matrix element using random matrix theory you can write. So there is some generic form of this matrix element, which is given by what appears here is this many-body level spacing delta p, which I showed earlier, which is exponentially small, and some spectral function of the bubble. Okay, and then there is some random number, and this omega is this transition, the energy of this transition that this bath supplies. Okay, to the transition of this bit, the local integrals of motion. So now, yes. You can do it. It's just you just take this. I mean, this thing will not matter. Yeah, it's just for some model you take some concrete. Okay, so now this Fermi golden rule rate. So you can now, of course, the Fermi golden rule rate will only work if you have a small enough level spacing, or in some sense, if the bath is continuum enough. Okay, and the way, so there is a way to check that. So the way you check that in Fermi golden rule, you calculate the matrix element, and you ask whether this matrix element is larger than the level spacing of the bath, which is giving you the Fermi golden rule. And that's the criteria that there will be a Fermi golden rule. Okay, so Fermi golden rule relies on this continuum of states, and you can check the continuumness of this state using this criteria. And once this is valid, then you will have a rate. Of course, that rate will not depend on this many-body level spacing or anything. You will calculate it eventually, some value. But the fact that there is a non-zero value depends on this criteria. And so now the point is that since this path has a very small level spacing, because it's a many-body path, you can think that reasonable coupling, with reasonable coupling, you can satisfy this criteria. So in other words, the local integrals of motion, which is closest to this path, will always thermalize with this path for any reasonable coupling, if you have sufficiently large path. If you don't have, then in the thermodynamic system, there will be some other place, there will be a larger path, which will satisfy this. Okay, so you can always satisfy it for a given system. Yes. Right. So that's a good question. So you are saying the transition is away from the bandwidth of the bath. That's what you are saying, right? So here they are assuming that the start with this bath is broad enough, and so you essentially need energy of this random field, right? So give the transition. So you are assuming that this bath is broad enough to cover this. So bath is first of all dense. The level spacing is dense enough, so you satisfy this, and the width of the bath is large enough so that you can make this transition. That's right, but ultimately here for this argument, only thing is matter is the single particle. See, I mean the argument only relies on the single particle width, bandwidth of this local spin, right? And the single particle bandwidth of this bath. So it doesn't rely on the many body bandwidth, right? Because I am doing at one at a time. So this disregard the whole system. So you first look at this this spin. Let's say it is in a Wiegmann field H, right? So you need an energy 2H. That you can always supply with a large enough bath, right? So disregard the whole thing. So this is an issue that when you go on with this process, what will happen? But we do one at a time. Okay, so that's the idea. So you do this. So now you can, let's say, so you can always satisfy this criteria, but if you satisfy this criteria, that means that now this local integrals of motion is part of this bath. So it has been absorbed in the bath. So the bath, in a sense, has become bigger because if there is a Fermi golden rule, the number of states in the bath is actually larger by a factor 2. So your level spacing has gone down by a factor half. Okay, so in some sense, it has become a more potent bath now once you absorb this. So now, if you assume that you can continue this process to some extent, meaning that up to some radius where you absorb all local integrals of motions by satisfying this criteria, because remember at each time your bath level spacing also becoming smaller. So then you can find out that if you grow this bath up to a radius r and then you look at the next LIOM, next local integrals of motion, then you can again try to find out this criteria using this renormalized level spacing of the path and this exponentially small coupling which is at a distance r. And what you will find that the criteria is something, the details are not very important, but the expressions for this will be this. So this criteria that you have to satisfy is exponential r to the power d minus r by xi. Okay, now as you can see that any dimensions greater than 1, this criteria will always be satisfied because you have a some term which is growing like some power of r which is higher than 1, and that has to compete with this exponentially small term, but this is all only in exponential in r. And as a result, the idea is that if you can continue this process up to some finite thing, then it will eventually, it will always continue for arbitrary large distances, and essentially means that this whole system will be destabilized by this. Okay, so that's the argument. Okay, so one important thing that I will come to just in few slides that so there is a so that's basically, so 1D of course that's not true. 1D these two things can still compete because 1D both will go as same power of r in the exponential. So the exponential either could be dominated by minus of r by xi or this positive r by 2. So there will be a transition there in 1D when this criteria could be satisfied or not. But in higher dimension, always this criteria will be satisfied, and as a result, your MBL will be unstable.
Sorry, Sumilan, this rho b of omega, that is this imaginary part of retarded Green's function, which this new thing added, or
yeah. So that's the important point. So I just come to that now. So yeah. So I'll come to that point. So what they try to argue is that when you do, so of course you are right. So this spectral function will change, right, when you add this thing. So what they try to argue using some sort of heuristic type of argument is that this spectral function will not change much as you do this process. Meaning the original spectral function of the GOE, even when you add this large layer around it, will almost be same. So that's the assumption in their argument. So we are actually going to test this assumption. So that's one of the things. That's why I have put it in red. And you're right. So that's the important point. Okay. Yeah, but it's the worst scenario for thermalization, right? So if Anderson localization is even unstable, then it's very unlikely an interacting insulator will be stable. No, experiments, you mean two-dimensional experiments? So first of all, there are very few now. And secondly, I'll show that actually all these arguments are somewhat academic exercise because the time scale that you need for a standard system will be huge. But this is a proof of principle. So we are saying that for an infinite system, there is no MBL eigenstate. That's what it is trying to prove. For practical cases, you might not be able to see it at all. Okay, I'll estimate some time scale if this is true. Okay, so let me just go a little faster now. So just to summarize what I said, so if you see in one dimension, what you can do, starting from different initial conditions, so you can plot this ratio, ratio of, so you can actually write down this, so I was talking about the ratio of the matrix element versus the level spacing, but you can convert it to the ratio of Fermi golden rule rate and level spacing, and this gives the same criteria. So you can always look at this Fermi golden rule rate divided by the level spacing and ask when it goes above 1 or goes below 1. Okay, when it stays above 1, when it goes below 1. And if you draw it in 1D, this is the generic situation. You can show that if your localization length is greater than something here, then always these curves actually monotonically increase, meaning that if you start with a bubble which is large enough, which gives the decay for the first LIOM, then it will always give decay to higher LIOMs which are further away. So this is just plotting this function, okay, for 1D. However, for cases if you start with a localization length which is smaller than some critical value, then this curve will be monotonically decreasing, And once they hit below 1, then it says that you can no longer satisfy Fermi golden rule. And for those situations, this bubble will not be able to work. Okay, so there is a transition in this in 1D. However, in higher dimension, this curve is actually non-monotonic. So it can initially decrease, it will initially decrease and then it will increase later. Now the criteria that you need here is that this minima never goes below 1. So once the minima goes below 1, when you are at stage of this absorption of this LIOM, as soon as it goes below 1, no longer it can carry this process. But what you can argue that if you have a critical bubble size, which is determined from the localization length, then this minima will be always greater than 1. Okay, that means if you start with a bubble size which is large enough, and that you will always be able to do for a thermodynamically large system, there will be always such a bubble. And that means in always you can essentially satisfy this criteria and this thing will be destroyed. However, as I told that if you try to estimate that what is the probability of this kind of rare region appearing in a system, then that probability will be exponential, exponentially small. So the distance between these bubbles will be exponentially large, and essentially that you can estimate what is the time scale over which you will see this effect of thermalization, and that time scale will be exponential to exponential. Okay, so extremely large, and for any realistic system, you will never be able to wait so long to see this effect. Okay, but okay, it's a question of principle that whether there is MBL in higher dimension or not. That's why we are discussing. Okay, so let me just, so this is the thing, and what, as Manoj pointed out, one of the issue that they are taking, one of the assumption they are taking is that even when you go to a distance r, this spectral function remain basically featureless, like a GOE that you started with. Now, question is how far this assumption is correct, okay, whether this is valid or not. So we are going to test this. So let me first test this assumption, this instability argument using some small system diagonalization. So what we do, we basically create the same system that I described, and now we are working here with spins. So you can do the same thing. You can define some localized spins here, which is essentially some spin in some random Zeeman field, which are these local bits. And the bath is some random matrix 2 to the power n cross 2 to the power n, which is in this basis of this spins in the bath. And then there is a coupling, which is again like exponentially decaying. So what we are going to do is we are going to do the same thing, that we take this bubble and you couple this local integrals of motion, and each stage you try to check this criteria, okay, whether it is satisfied in exact diagonalization. And that we will also do in 2 dimension. So of course, these system size are extremely limited. Limited. So you can start with, let's say, bubble size of 8 in 8 spins, and then we are limited essentially up to 6 or 8 more LIOMs that you can add. So that reaches the ability to do at least standard exact diagonalization. So we are limited by system size, but even within that, we can try to see that whether these assumptions and arguments are actually valid or not. So that's what we are going to do, and what we check here is that as we add these local integrals of motions, we essentially calculate the spectral function for a given eigenstate that I mentioned, okay, earlier. So basically assumes that I first add this circle in 2 dimension. And then I calculate the spectral function of this and look at it, and then I add another and again look at the spectral function. So from this spectral function, what you can extract is you can extract this Fermi golden rule decay rate, which is essentially, so initially when these LIOMs are decoupled, they are like one spin in a random magnetic field. So they have 2 peaks, okay, 2 sharp delta function peaks for the spectral function. Now when you have coupling to the bath, and the coupling, if it is potent, then this will be widened. This peak will be widened, broadened, and this broadening is essentially this Fermi golden rule rate. Okay, and what you can do, you can calculate the level spacing of this full system, and you can just calculate the ratio of this broadening and the level spacing, and you can just plot and compare with this. So what you find is that extremely good agreement with this argument that as you, so this is in one dimension, so you see again see the same thing, that there is a transition. So there is a localization length above which all these curves actually go up. So essentially meaning that those will delocalize the system. But if you are below certain localization length, then all of them go down and then hit 1. And once this hit 1, then there is no rate. Okay, so the peaks just remained like this sharp poles. So these are these localization length numbers. Oh no, sorry. So 4, 2. No, not strength of the interaction. Yeah, I don't. Yeah, okay, I don't remember now. I mean, but I think okay for this plots. I mean, okay, essential thing is this this localization length, and there is a transition as a function of this. Yeah. Okay. So now if you look at 2 dimension, then you see exactly the same thing that you saw here, that there is a non-monotonic dependence. So there are these steps like feature, that's because you are adding in these concentric circles. So each time you add a circle, there is a kind of step which you see here. But other than that, the basic feature is this, that for some cases it goes below this line 1, and as soon as it goes below 1, then this stops. And as soon as it goes above 1, then they eventually increase. And these dashed lines are effectively what you calculate from this theory. Okay, so you can put the calculation from the theory, and these lines are exact diagonalization results. And as you can see that they almost exactly agree. So within the small system size, even though they took kind of a crude assumptions of this Fermi golden rule rate and things like that, it seems like when you do this calculation, sort of ab initio, they seems to agree. Okay, so that's the thing. So now, of course, it says that this, at least if you calculate the Fermi golden rule rate, this is agreeing. You can ask some further question. You can ask, for example, this local integral of motion you added to this thing is essentially entangled with this path or not. Okay. So if they are completely entangled, then they will have entanglement entropy of log 2, and this you can test again by exact diagonalization. And you what you see, just to summarize, that all the cases where Fermi golden rule rate holds, all the cases these are fully entangled with the path. Okay, for large system size. So that means that when Fermi golden rule rate hold, also they get completely entangled. That means they are really thermalizing. Okay. And you can do certain other things. I will not go into the detail of this. You can calculate some kind of many body Thouless conductance. And again, all the cases where Fermi golden rule rate holds, from this criteria also, you will see that all these bubbles are actually thermalized and satisfies the criteria. So it means that, first of all, the Fermi golden rule argument is working even in exact diagonalization. Second, when they are working, they are also showing that indeed all these local integrals of motions are thermalizing with the bubble. Okay, and so in some sense you are excellent agreement with this thing. So if it really true for larger system, then if something else doesn't happen, then that means that MBL will be unstable in a higher dimension. There could be no MBL phase. Okay, so that's the summary, that for small system size, whatever you can capture with ED, that's the thing. But now we are going to do a slight a calculation which is indirect. Directly will not tell us about localization, but we'll try to test this assumption which Manoj pointed out, which is about the spectral function. Okay, so that's what. So the question is that if you go to really large systems. So the thing also was mentioned that what about this bandwidth and the fact that you are adding very random energy scales to the systems, all sorts of energy scale as you go to larger and larger. How does it affect this spectral function? Okay, so is it true that when you add a large number of LIOMs, that this is still this original GOE spectral function remains same? So in exact diagonalization, we cannot test it because you can only do very small systems. So what we are going to do, again, we are going to define a toy model. Since I don't have much time left, so I'll just go over the details of this model very quickly. So what you define? So can I just take 3 minutes? We define. We use some model where you describe this bubble using some Hubbard model, some infinite range Hubbard model, and then the setup is same, that you couple to some this local integrals of motions around it. And however, I mean, we want to have some control calculation in some sort of large chain. And as a result, you have to define the coupling in a certain way, which has the main essence of this calculation. However, which is you can act, I mean, so that it remains tractable. Again, I will not be able to go into the detail. But what happens is that this problem you can essentially reduce to a effective Anderson impurity problem. And in this impurity problem, we can't really, or we have not calculated the eigenstate spectral function that I mentioned. But what I'll try to argue that even the thermal spectral function has a large effect of this insulator. That's what I'm going to discuss. So just to summarize, you can solve this problem that I defined using some sort of DMFT techniques, which is used to solve this bubble and all. So the details are not important, but what you can do eventually, you can get the thermal spectral function, and you can at least ask whether the thermal spectral function is at least getting changed by a large amount or not. Okay, we can't look at the eigenstate spectral function. So what you see that indeed, if you have very small coupling, so what is shown here is the same setup, and we are looking at this Bath spectral function, which was appearing in these equations, and you look at a function of this number of LIOMs that you add, this M. Okay, and we can do it for a huge number of LIOMs, like some 1 lakh or something. I mean, you can go even larger. So for this calculation, it doesn't matter. So what you find that if you have small coupling, then so you start with some spectral function which is like that, and when you start adding these LIOMs, then you of course get this ruggedness which are coming from the poles of this insulator. But even if you go to very large value, this green one is the like a converged spectral function, which stays basically same as what you started with. And as a comparison, we have compared the spectral function what you would have got for a non-interacting bubble, meaning where the U is 0. And you can see that they are very different. So it says that the bubble, the interacting bubble that you started with, the spectral function remains more or less same. But when you increase the coupling slightly larger, and but not much large, so it is still within the Fermi golden rule argument that they use. But you find that when you add large number of LIOMs, actually the spectral function completely changes. Okay, and essentially in the low energies, it essentially becomes exactly like the spectral function of the Anderson insulator. That means that this thermal spectral function, this sort of behavior, is completely destroyed when you add these many poles, spectral poles, when they are coupled. So again, so we can't really rule out whether this state is localized or thermal, but at least what it is telling that the spectral function always remaining same is not true. At least even for the thermal spectral function, it is not true. So most probably for if you could look at the eigenstate spectral function, it will not be true. Okay, so this is a possible route to failure of this argument. So we don't know, I mean, whether this is really the actual failure or not, but this is a probable failure. So with that, I will just end. I mean, so these are some caveats, but just to summarize. So what I mainly discussed is this instability arguments, which tries to argue about this non-perturbative effect of rare region. And what I found that from exact diagonalization, it sort of supports this picture, which is called this thermalization avalanche. However, some of the assumptions of this theory, which, for example, the main assumption that the spectral function remains same, may not be valid. But we don't have a way to really tell for such large system sizes whether the systems are actually localized or not. And another thing is that this rare region argument may not apply for quasi-periodic system, although there is some arguments there too. So in those systems, maybe higher dimensional MBLs are possible, even if this argument is correct. Okay, with that I'll stop.
Yes, thanks, Sumilan. Questions?
Yeah.
So, do you have any data on how this spectral weight shift is affected as you change the number of degrees of freedom in this bubble?
In the exact diagonalization.
Yeah.
Yeah, we have a data I have not shown. So what you see that again you can look at this eigenstate spectral function there, and you see all the cases where Fermi golden rule rate holds, the eigenstate spectral function is thermal, and all the cases where Fermi golden rule rate doesn't hold, the spectral function become like a localized thing. So once you go to the localized regime, then they just become some peaks. For the bubble, for the bubble. So the system size that we have studied, there the effect on the bubble is not very large. So because we can only add like 8 bubble spins and let's say 8 thing, and at extent the bubble was not changed much.
Questions? So maybe I had one question. So in the case where you showed that the thermal spectral function was more or less the same,
Right.
But that doesn't, I mean, the eigenstate spectral function can be quite different, right?
Yeah, it could be localized in that case.
So then why is that useful even if it is same? I mean, because what goes into
it is not useful. So even if you find it same, right, you are right. So even if I find it same, it doesn't really tell that this system is localized or not.
Okay.
So that we cannot really say. Only thing that we are saying is that this assumption may not be valid. Now, I mean, either cases we can't really say either ways that whether the localization versus thermal, that debate, we are just testing this assumption. So some cases the assumption is at least right, whatever we can calculate, and some cases not.
Okay. More questions? Okay, if not, let's thank Sumilan.